In our previous video, we looked at non-homogeneous linear differential equations of higher order with constant coefficients. And we found out if the non-homogeneous equation equaled a nice function like an exponential, a sine or a cosine, or a polynomial, we could guess at the form with undetermined coefficients of the particular solution. But what do we do if it's not one of those nice equations? Our question today is going to be, how do we solve for y particular when we cannot guess the particular solution form? And the answer to that question is we're stuck using a bit more tedious method, though not too difficult, called the variation of parameters. And I'm not going to go too deep into the theory here, but I'll kind of surface level talk about it. If the system, or if the differential equation y prime prime plus p of x y prime plus q of x y equals f of x has a complementary solution of y complement equals c1 y1 plus c2 y2, then y particular is of the form y particular is equal to a u1 y1 plus u2 y2, where u1 and u2 are functions of x, or our independent variable. Now, we can place this solution into the original differential equation that we have in number 1, and doing a little bit of work, it leads to the system of equations y1 times u1 prime plus y2 times u2 prime equals 0, and y1 prime u1 prime plus y2 prime u2 prime equals the same function that the differential equation equaled. And the derivation of this system of equations that we have here in number 2 is explained in your book, so you can take a look at where it comes from in your book. But what's important for us is solving this system using Craimer's rule. Craimer's rule is a nice trick to solve any systems of equations using determinants. Leads to u1 prime is equal to the opposite of y2 times the function divided by the Wronskian, and u2 prime is equal to y1 times the function, positive this time, divided by the Wronskian. And I'll even say where the Wronskian is equal to the determinant of the solutions and their derivatives. And we've seen that Wronskian before when we were talking about linearly independent functions. So now we have a formula to help us solve for u1 and u2 that we can plug into the y particular form to find y particular. As this process is the same regardless of what that f of x function is, it even works for the types of equations we saw in our previous video. We only really need to do one example to see this process worked out, and then I'm going to give you some time to practice on the assignment. So we're going to solve y prime prime minus 4y prime plus 4y is equal to x plus 1 e to the 2x. And we could probably use the method of undetermined coefficients on this one to solve, but let's solve it with variation of parameters. With variation of parameters, the first thing we need to do is find y complement, so we know what that y1 and y2 are. Well, using our auxiliary equation, this is m squared minus 4m plus 4 equals 0, which factors to m minus 2 squared equals 0. So m equals 2, and y complement is equal to c1 e to the 2x plus c2x e to the 2x. After we found y complement, we can now find the Wronskian, where the Wronskian is the determinant of our two solutions, e to the 2x and x e to the 2x. That's the first row. The second row is the derivatives, 2e to the 2x, and we have a product rule here, so e to the 2x plus 2x e to the 2x. Calculating that determinant, the first diagonal is e to the 2x times e to the 2x plus 2x e to the 2x, minus the second diagonal, which is 2x e to the 2x times e to the 2x. And simplifying by distributing, we have e to the 4x plus 2x e to the 4x minus 2x e to the 4x when I add the exponents. Well, that's nice because those two terms add up to 0 at the end, and so my Wronskian is just equal to e to the 4x. All right, now that I know my Wronskian, we can find u1 prime and u2 prime using those formulas we had in number 3 up above. That tells me that u1 prime is equal to negative y2, which is x e to the 2x, times the function. Well, the function is x plus 1 e to the 2x divided by my Wronskian of e to the 4x. And u2 prime is equal to the first solution, e to the 2x, times the function, x plus 1 e to the 2x, divided by the Wronskian, e to the 4x. I'm going to simplify these a little bit. What's nice is e to the 2x times e to the 2x is e to the 4x, which is going to divide out with the denominator in both of these. So these come out to much nicer. u1 prime is equal to, when I distribute, negative x squared minus x, and u2 prime is just x plus 1. Now that I have those prime, we can integrate them to get what u1 and u2 actually are to find my y particular. If u1 prime is equal to negative x squared minus x, I can integrate dx, both of those. And u1 is equal to negative 1/3 x cubed minus 1/2 x squared. If u2 prime is equal to x plus 1, I can integrate those dx to get u2 is equal to 1/2 x squared plus x. Put those together to get y particular. Y particular is equal to, I'll actually copy the formula here just because it's off my screen. The formula was u1 y1 plus u2 y2. And if you remember, it's off my screen, but my first solution for y was e to the 2x. And my second solution for y was x e to the 2x. So putting all these pieces together, y particular is equal to u1, negative 1/3 x cubed minus 1/2 x squared, times y1, which is e to the 2x, plus u2, which is 1/2 x squared plus x, times y2, which is x e to the 2x. Doing a little cleanup by distributing through, we get negative 1/3 x cubed e to the 2x minus 1/2 for y particular, x squared e to the 2x plus 1/2 x squared, x cubed, sorry, e to the 2x plus 1x squared e to the 2x. And finally, combining like terms, on the x cubes, negative 1/3 plus 1/2 is 1/6. X cubed e to the 2x. And negative 1/2 plus 1 is plus 1/2 x squared e to the 2x. And now we've got our y particular using the method of variation of parameters. From up above, if you remember all the way back in number 1 from this example, this is just copying what we had for y complement up above. We had c1 e to the 2x plus c2 x e to the 2x for our y complement. And so if I want to actually say what y equals, it's y complement, c1 e to the 2x plus c2 x e to the 2x plus y particular, 1/6 x cubed e to the 2x plus 1/2 x squared e to the 2x. And now we have our general solution using the method of variation of parameters. At this point, if we had some initial conditions, we could go back and solve for C1 and C2 to match those initial conditions. But for now, it's your turn to practice this variation of parameters method. Every single problem can be solved using this exact same method. So you want to get comfortable with it. You want to know the equations for u1 prime and u2 prime so that you can develop that particular solution, regardless of what the non-homogeneous differential equation equals. Good luck as you practice.